All right, this video is going to show us some basics with logarithms. So remember, we can go from log to exponent form and from exponent form to log form. So let's try that. With our log form up here, we can use the snail method. So we start at the base and we say 2 raised to what power? So 2 raised to the third power equals this number, equals 8. So the base raised to what power equals 8. And we could check that in our calculator. 2 to the third power does equal 8, so we know that we did that properly. If we try this example, even if there's variables, it's still the exact same property. So I start with my base. Remember that your form for logarithms, that is always the base. So the base raised to what power? 4 raised to the y power equals 16. So we could solve for y, if we think about it, 4 times 4 is 16, so y could equal 2. But we'll do more of that later. And then it's the same idea if we're going to go backwards from exponent to log form. We can't use the snail method on what's written right here, but we can use the snail method to kind of help us think of it. So I always like to write a log, leave some space, and then put an equal sign. So I told you up here that the base of the log is that little number at the bottom. Well, for an exponent, this is the base. It's the base of the exponent. So this base is the same base for the logarithm. So the base here is 7, so the base of the log is 7. And then if I think of the snail method, it says 7 raised to what power? What power? Power is like exponent. I see here my exponent is 2. So 7 raised to the second power equals 49. So 49 would go right here. We can try the exact same strategy over here. I'm going to write out log and leave some space. So my base here is 4. This is the base of the exponent. So the base of my log is 4. And it says 4 raised to what power? What is the power? Well, the exponent here is 1/2. So 4 raised to the 1/2 equals 2. So there's 2 properties that we want to make sure we remember about logarithms. They're going to come in handy, especially if we were to convert these two from log form to exponent form. So when I look at this, I notice there's no base written under this first one, and there's no base on the ln over here. So remember that ln, this is an L, not an I or a 1, is the natural logarithm. So it has the same properties as log. It just uses the value of e instead. So a log with no base has a base of 10. So the way I remember that is if I write the word log while looking at the L and the O, it looks like a 10. So this problem is actually log of 5x equals 3. It's log base 10. So to turn this into exponent form, I start with my base, 10 raised to the third power equals 5x. And then it's a similar concept. So talking about this natural logarithm again, I said that it has a special relationship with e. So an ln with no base has a base of e. So what we can do with this problem is rewrite it and write in our little e for our base here. I don't really have a good memory trick for this one, but if you can remember that the log is 10, then process of elimination means ln has to be the e, if you can remember those two things. So if we wanted to practice switching this, we would have e raised to the 5th power equals all this stuff right here, e to the 5th. And yeah, e to the 5th equals e to the 5th. That makes sense to me. All right, we can also use this snail method to help us evaluate logarithms. So what I would ask you to do for these is evaluate or simplify. So it means we need to solve. So we have log base 2 of 32 equals, I don't know. Well, there's two strategies here. So the first strategy would be snail method. So if I use the snail method, I start with my base and I say 2 raised to what power? Well, in this case, we don't know the power. It's my box here. So I'm just going to write my box equals 32. So now what I could do is open up Desmos. So I'm looking for 2 to some power equals 32. So I could try just typing in some values. Not 2 to the 3rd, not 2 to the 4th. 2 to the 5th equals 32. So 5 must be my answer. So I must fill this in with a 5, meaning that would be my answer. The other strategy you can do, if you don't want to use the snail method here, is use Desmos. The only catch is if there are variables, this isn't going to work. So it has to be a problem with no variables. So like the problems down below wouldn't work. So if we go to Desmos, we can just type in this original expression that we had, log base 2 of 32. So I type log, I hit shift and minus, base 2 of 32, and I just see that that equals 5. So I didn't even have to use snail method, it just tells me the answer. So if we look at the next one, we'll do it backwards this time. Let's try Desmos first. Log base 5 of 625. Log base 5 of 625. Looks like the answer here is going to be 4. So we could check our work. I'm going to use snail method to help me check my work. So if I start with my base, I say the base raised to the 4th power equals 625. Well, let's check it. 5 raised to the 4th power. Ta-da! Equals 625. So that does make sense. All right, last thing about log form and exponent form. If we look at both of these, we see e as a base of the exponent, base of exponent. But then when we look in the exponent, we have ln, which we know has a base of e, base of ln. If we look at this other problem, again, we've got 5 as the base of this exponent. But then if we look at the exponent itself, 5 is the base of the log. So anytime the base of the exponent equals the base of the log, or ln, they cancel. And this is because these are opposite operations. It's like if we have x squared and we take this square root and squared cancel, and so we're just left with x. Opposite operations. So in this case, this e raised to the ln of e, those cancel, and we're just left with whatever the remainder is. So here it just is 4x. And on the right, 5 raised to the log base 5 of 11, those, the exponent and the log cancel, and we're just left with the 11 as the final answer.